Welcome! In this session, we'll be exploring problem number 773, titled Sliding Puzzle. This classic problem challenges us to solve a sliding puzzle by finding the fewest number of moves to transform the board into its target configuration. We'll analyze different approaches and discuss their efficiencies. Let's dive in. In this problem, we are working with a 2x3 sliding puzzle board. The board is made up of 6 tiles, where 5 of them are numbered from 1 to 5, and 1 tile represents an empty space, which is denoted as 0. The goal is to arrange the tiles in a specific target state, 1, 2, 3, 4, 5, 0. To do this, we can move the empty space by swapping it with one of its neighboring tiles, which can be above, below, to the left, or to the right of it. The challenge is to determine the minimum number of moves required to transform the given starting state of the board into this target configuration. If it's not possible to reach the target state, we need to return -1. The input for this problem is a 2D integer array representing the initial state of the puzzle, and the output is an integer indicating the minimum number of moves or -1 if the target state cannot be achieved. To better understand the problem, let's look at some examples. For the first example, the input board is 1, 2, 3, 4, 0, 5. The target state is 1, 2, 3, 4, 5, 0. Here, we can achieve the target configuration in just one move by swapping the empty space, represented by 0, with the tile to its right. Therefore, the output is 1. In another example, the input board is 1, 2, 3, 5, 4, 0. In this case, it is impossible to rearrange the tiles to match the target state, so the output is -1. Now, let's consider a more complex case. For the input board, 4, 1, 2, 5, 0, 3, the target state is again 1, 2, 3, 4, 5, 0. To transform the board into the target configuration, we need 5 moves. First, we swap the empty space, 0, with the tile 3. Then, we swap it with 2, followed by 1. Next, we swap it with 4, and finally, we swap it with 5. After these 5 moves, the board matches the target configuration, so the output for this example is 5. This problem has a few constraints and edge cases to consider. The board is always a 2x3 array, and each value on the board is unique and ranges from 0 to 5. If the board is already in the target state, no moves are needed, and the output should be 0. Additionally, there may be cases where the configuration of the tiles makes it impossible to reach the target state, in which case the output should be -1. Finally, the position of the empty space, 0, at the start can significantly impact the solution. For example, if 0 is in a corner or along an edge, it might limit the possible moves, influencing the path to the solution. To tackle the sliding puzzle problem, the most straightforward idea is a brute force approach using exhaustive search. Here, we simulate every possible valid move from the initial board configuration and check if the goal state is reached. This can be implemented using recursion or a depth-first search approach. Since the puzzle involves only 6 tiles, the number of possible states is finite, and each state can be represented as a string for easy comparison. However, while this method is simple to understand and implement, it has significant limitations. Without proper tracking, the algorithm risks revisiting the same board states, leading to redundant computations. This inefficiency, coupled with the large branching factor of possible moves, makes it computationally expensive. The time complexity for this approach can be factorial, which is impractical for real-world scenarios, especially as the search depth increases. While it serves as a baseline, its inefficiency highlights the need for more optimized solutions. To improve on brute force, we can use a breadth-first search, or BFS, which explores all possible configurations level by level. This ensures that the shortest path to the goal state is found, making it an optimal choice for problems like this. BFS represents each board configuration as a string, such as 1, 2, 3, 4, 5, 0, to simplify comparisons and enable efficient state tracking using a set. The empty space, represented as 0, determines the valid moves by swapping with its adjacent tiles. By pre-computing these possible moves for each position, we can further reduce the computational complexity. The process involves enqueuing the initial board configuration along with the move count, starting at 0. For each state queued, we compute all possible valid moves and check if any of these result in the goal state. If so, the move count is returned. Otherwise, the new states are enqueued for further exploration. If all possibilities are exhausted without reaching the goal, the puzzle is deemed unsolvable, and we return -1. This systematic layer-by-layer exploration ensures efficiency and avoids redundant paths. BFS comes with its own set of trade-offs. On the positive side, it guarantees the shortest solution and avoids revisiting states, making it significantly more efficient than brute force. However, it does require additional memory to store visited states. The time and space complexity are both factorial in the worst case, but in practice, the pruning of redundant computations makes it far more manageable. Another alternative worth considering is the A** search algorithm, which enhances BFS by introducing a heuristic to prioritize states closer to the goal. A common heuristic is the Manhattan distance, which calculates how far each tile is from its target position and sums these distances for the entire board. A* combines the actual moves taken, represented as G, with the heuristic value, represented as H, to prioritize states with the smallest combined cost, F equals G plus H. This approach often outperforms BFS for solvable puzzles due to its better prioritization. However, it comes with its own trade-offs, including the need for a carefully designed heuristic and higher memory usage due to the priority queue. While A* shares a similar worst-case complexity with BFS, its practical performance can be much faster. For this problem, we chose breadth-first search as our strategy due to its balance between simplicity, optimality, and efficiency. While A* is theoretically faster, BFS is easier to implement and perfectly sufficient for the small state space of a 6-tile puzzle. Its guarantee of finding the shortest path aligns well with the problem's requirements, making it a reliable choice. By systematically exploring each state and using a set to track visited configurations, BFS avoids redundant computations and ensures all possible paths are explored in the most efficient order. The main trade-off is its memory usage, which is higher than brute force due to the need to store visited states. However, given the limited number of possible configurations, this requirement is manageable. BFS strikes a balance between practicality and performance, making it a well-suited and widely accepted choice for solving sliding puzzle problems. The sliding puzzle problem challenges us to solve a board game where tiles are rearranged to achieve a specific goal state. The board is typically represented as a 2D array, with one tile missing to allow movement, identified as the empty space. The objective is to determine the minimum number of moves required to transform the initial configuration into the goal configuration. For example, the board could start as 1, 2, 3, 4, 0, 5, and the goal might be 1, 2, 3, 4, 5, 0. If the goal state cannot be reached, we return -1. To solve this, we begin by flattening the board into a string for easier manipulation, such as converting 1, 2, 3, 4, 0, 5 into the string 1, 2, 3, 4, 0, 5. The goal state, similarly, would be 1, 2, 3, 4, 5, 0. Using BFS, or breadth-first search, is ideal here because it explores configurations layer by layer, guaranteeing that the first time we reach the goal state, it is with the minimum number of moves. To set this up, we use a queue to store board states along with their respective move counts. Each queue entry is a tuple of the current board state and the number of moves taken so far. In addition to the queue, we use a visited set to keep track of states we've already processed, preventing redundant computations and infinite loops. We also pre-compute an adjacency list to represent valid moves for the empty tile's position, optimizing state generation. For example, on a 2x3 board, if the empty tile is at the top left, index 0, it can move to indices 1 or 3. If it's at index 1, it can move to indices 0, 2, or 4, and so on. With these preparations, we implement the BFS algorithm. First, we enqueue the initial state with a move count of 0. Then, while the queue is not empty, we dequeue the front entry. If the current state matches the goal state, we return the move count. Otherwise, we generate all possible new states by moving the empty tile to its valid adjacent positions. Each new state is created by swapping the 0 with the tile at the target position, converting the result back into a string. If the new state hasn't been visited yet, we mark it as visited and enqueue it with an increment move count. If we exhaust the queue without finding the goal state, it means the puzzle is unsolvable, and we return -1. BFS is the perfect choice for this problem because it guarantees the shortest path in an unweighted graph, ensuring that the first time we reach the goal state, it's with the fewest moves. Using a visited set is crucial to prevent revisiting the same state, which would waste computational resources and could lead to infinite loops. Pre-computing the adjacency list of valid moves for the empty tile allows us to efficiently generate new states during the BFS traversal. The key data structures here include the queue, which stores the board configuration and move count, the visited set to track process states, and the adjacency list to encode valid moves for the empty tile. For complexity, the worst-case number of states is the factorial of the number of tiles, because each state is a unique permutation. For example, a 2x3 board has 6 equals 720 possible states. Generating neighbors for each state takes n time, where n is the number of tiles, so the time complexity is n*n. The space complexity is also n, as both the queue and the visited set can hold up to this many states. These insights guide us toward writing an efficient solution. There are several edge cases we need to handle in this problem. First, an unsolvable puzzle can be identified by counting inversions in the initial state. An inversion occurs when a larger tile precedes a smaller one in the flattened board. If the number of inversions is odd, the puzzle is unsolvable, and we can immediately return -1. Second, if the initial state already matches the goal state, we return 0 without further computation. For larger boards, memory usage can become a bottleneck due to the exponential growth of possible states. In such cases, optimizations like bidirectional BFS can be considered to reduce both time and space complexity. To illustrate all these concepts, let's walk through some pseudocode. We start by flattening the board into a string and defining the goal state 123450. We also pre-compute the adjacency list for valid moves based on the board layout. Using a queue, we initialize with the starting state and a move count of 0, and we maintain a visited set to avoid reprocessing states. The BFS loop proceeds by dequeuing the front state, checking if it matches the goal, and generating new states by moving the empty tile to its valid neighbors. To generate new states, we identify the index of the empty tile, represented by 0, and iterate over its valid neighbors using the pre-computed adjacency list. For each neighbor, we create a new state by swapping the empty tile with the target tile. This new state is converted back into a string to maintain consistency. If this new state hasn't been visited yet, we add it to the visited set and enqueue it with the move count increment by 1. The process continues until we find the goal state or exhaust the queue. If the queue is exhausted, it means the puzzle is unsolvable, and we return -1. This implementation ensures that we explore all possible configurations in the most efficient way, leveraging BFS to guarantee the shortest path. The algorithm structure is both systematic and scalable for small to moderately sized boards, making it an effective solution for the sliding puzzle problem. To solve the sliding puzzle problem, we start by importing the deque from the collections module because we'll use a breadth-first search approach. We define a class solution and implement a method sliding puzzle that takes the board as input. The goal is to transform the board into the target configuration, which is represented as the string 123,450. To work with the board efficiently, we flatten it into a single string and locate the position of the empty space, represented by 0. Next, we define a dictionary called moves which maps each index of the flattened board to the list of indices it can swap with, based on the puzzle's layout. For instance, if the empty space is at index 0, it can swap with indices 1 and 3. This accounts for the puzzle's movement constraints. Now, we use a queue to perform the breadth-first search. The queue stores tuples containing the current board state, the position of the empty space, and the number of moves taken so far. We also maintain a visited set to keep track of states we've already processed. Initially, we add the starting state to both the queue and the visited set. Then, we enter a loop to process each state in the queue. At each step, we dequeue an element to analyze the current state, the position of the empty space, and the associated move count. If the current state matches the target configuration, we return the move count, as that represents the minimum number of steps required to solve the puzzle. Otherwise, we explore all possible moves for the empty space based on the moves dictionary. For each valid move, we create a new board state by swapping the empty space with the adjacent tile. This is done by converting the current state string into a list, performing the swap, and then converting it back into a string. If the new state hasn't been visited yet, we mark it as visited and add it to the queue, along with the updated position of the empty space and the increment move count. This process continues until the queue is empty. If we exhaust all possibilities without finding the target configuration, we return -1, indicating that the puzzle is unsolvable. This approach ensures that we explore all possible states in the shortest path first, making it an efficient way to solve the problem using breadth-first search. In this Java implementation, we begin by defining our sliding puzzle method, which takes a 2D array board as input. The goal is to transform this board into the target configuration, represented as the string 123,450. To achieve this, we first convert the input board into a string format using a string builder. This string representation allows us to manipulate the board state more easily during the search process. Next, we define a map called moves to represent the legal moves for each index of the board. Each key in the map corresponds to a position on the board, and the associated value is an array of indices where the empty tile, represented by 0, can move. After setting up the moves, we initialize a queue for our breadth-first search and a set to track visited states. The queue is initialized with a state object that represents the starting configuration, including the board string, the position of the empty tile, and the initial step count of 0. By adding this starting state to the queue and marking it as visited, we're ready to begin exploring potential solutions. The core of the algorithm is the breadth-first search loop, which continues as long as the queue is not empty. At each step, we retrieve the current state from the queue using poll. If the current board configuration matches the target configuration, the method immediately returns the number of steps taken to solve the puzzle. Otherwise, we generate all possible next states by iterating over the valid moves for the position of the empty tile. For each move, we swap the 0 tile with the adjacent tile to create a new board configuration. This is done by converting the current board string into a character array, performing the swap, and then converting the array back into a string. If this new board configuration hasn't been visited yet, we mark it as visited and enqueue a new state object representing this configuration, the updated 0 position, and an increment step count. This process ensures that all possible configurations are explored systematically while avoiding redundant work by skipping already visited states. If the queue is exhausted without finding the target configuration, the method returns -1 to indicate that no solution exists. Finally, the implementation includes the definition of the state class, which is a simple helper class to encapsulate the state of the puzzle at any point during the search. It consists of 3 fields: board, representing the current board configuration as a string, 0pos, indicating the position of the empty tile, and steps, which tracks the number of moves taken to reach this state. The constructor initializes these fields, allowing us to easily create new state objects during the search process. By organizing the state information in this way, the algorithm remains clean and efficient, as each state object contains all the necessary data for processing and generating subsequent states. To solve the sliding puzzle problem, we use a breadth-first search approach. Let's begin by looking at an example with a solvable case. The input board is 1, 2, 3, 4, 0, 5. First, we flatten the board into a string start equals 1, 2, 3, 4, 0, 5 for easier manipulation, and the target state we need to reach is 1, 2, 3, 4, 5, 0. We initialize a queue with the tuple start 4, 0, where 4 represents the position of the 0, or empty tile, and 0 is the step count. We also maintain a visited set to track states we've already processed, starting with 1, 2, 3, 4, 0, 5. Now, we start our BFS. In the first step, our current state is 1, 2, 3, 4, 0, 5, the 0 is at position 4, and we have taken 0 steps so far. From position 4, the 0 can move to positions 1, 3, or 5. For example, swapping the 0 with position 1 results in the state 103425, which we add to the queue as 103425, 1, 1, and mark as visited. Next, swapping the 0 with position 3 results in the new state 123045, which we also add to the queue as 123045, 3, 1, and mark as visited. Finally, swapping the 0 with position 5 gives the state 123450, which is our target. This state is added to the queue as 1234505, 1 and marked as visited. In the next step, we dequeue the state 123450. Here, the 0 is at position 5, and the step count is 1. Since this matches our target state, we stop the search and return 1 as the minimum number of moves needed to solve the puzzle. The final output for this example is 1. Now let's consider an unsolvable case. The input board is 1, 2, 3, 5, 4, 0. Flattening this board gives the starting state 123540, while the target remains 123450. We initialize the queue with 123540, 5, 0, where 5 is the position of the 0, and the visited set starts as 123540. At step 1, the current state is 123540, with the 0 at position 5 and 0 steps taken so far. From position 5, the 0 can move to positions 2 or 4. Swapping the 0 with position 2 gives the state 120543, which we add to the queue as 120,543, 2, 1, and mark as visited. Similarly, swapping the 0 with position 4 results in the state 123504, which we add to the queue as 123504, 4, 1, and mark as visited. In step 2, we process the state 120543, where the 0 is at position 2 and the step count is 1. From position 2, the 0 can move to positions 1 or 5. Swapping with position 1 produces the state 102543, which is added to the queue as 102543, 1, 2, and marked as visited. Swapping with position 5 gives the state 123540, but since this state is already visited, we skip it. We continue exploring all states in the queue. Eventually, all possibilities are exhausted without reaching the target state. This confirms that the puzzle is unsolvable, and we return -1 as the result. The final output for this example is -1. Finally, let's look at a simple case where the puzzle is already solved. The input board is 1, 2, 3, 4, 5, 0. Flattening this board gives the starting state 123450, which is the same as the target state. We initialize the queue with 123450, 5, 0, and the visited set is 123450. At step 1, the current state is 123450, with the 0 at position 5 and 0 steps taken. Since the current state matches the target state, we immediately stop and return 0, indicating no moves are needed. The final output for this example is 0. To analyze the time complexity of this problem, we start by considering the breadth-first search approach used to explore all possible puzzle states. The number of possible arrangements of the 6 tiles in a 2x3 grid is 6 factorial, or 720. However, because only half of these configurations are solvable based on the parity of inversions, the total number of valid states is reduced to 360. When applying BFS, the algorithm may explore all 360 valid states in the worst case. For each state, the empty tile can move in up to 4 possible directions when it's in the center, but typically only 2 or 3 moves are possible depending on whether the empty tile is at the edge or in a corner. On average, this results in 3 new states being generated per state. Multiplying this branching factor by the total number of valid states gives us 360 times 3, or 1080, as the total number of state transitions. Since creating a new string for each state and performing set membership checks are constant time operations due to the fixed string length, these operations don't increase the asymptotic complexity. Therefore, the overall time complexity is determined by the BFS traversal itself, which generates 1080 transitions in the worst case. The time complexity for BFS can be summarized as V*E, where V represents the number of valid states, which is 360, and E represents the average branching factor, which is about 3. Multiplying these gives 1080, and since this value is based on a fixed state space and branching factor, it simplifies to 1 in big O terms. Now, for space complexity, the key factor is the data structures used during the BFS. The visited set is crucial to avoid redundant state exploration, and in the worst case, it stores all 360 valid states. Each state is a string of fixed length 6, resulting in a memory usage of 360 times 6, or 2160. The BFS queue is another major contributor to space usage. At its maximum, the queue size corresponds to the branching factor at the deepest level of the BFS tree, which is roughly half the total state space. This gives 3 times 360 divided by 2, or 540, as the maximum queue size. Each queue element includes the state string, the position of the empty tile, and the step count, which totals 8 units of storage per element. Multiplying this by the maximum queue size gives a total memory usage of 4,320 for the queue. Finally, other minor data structures, such as the moves dictionary, require negligible space and contribute 1. Adding up the contributions from the visited set in the BFS queue, the total space complexity becomes 2,160 plus 4,320 plus negligible overhead, which simplifies to 6,480. Since the number of states and the associated storage requirements are constant for this problem, the space complexity is also 1 in big O terms. Comparing this approach to a brute force solution highlights the efficiency of the optimized BFS. A naive brute force method would generate all 720 permutations of the puzzle, check each one for solvability, and then compare it to the target state. While this has the same asymptotic time complexity of 720, the constant factors are much larger due to the inclusion of invalid states. In contrast, the BFS approach is more efficient as it restricts exploration to solvable states and avoids reprocessing using the visited set. This eliminates unnecessary computations and keeps the effective time complexity proportional to the fixed state space size. In terms of best, average, and worst case scenarios, the BFS algorithm is highly efficient. If the puzzle is already solved, the algorithm terminates almost immediately, requiring 1. For an average input, it explores a portion of the fixed state space, which still results in 1. Even in the worst case, where all valid states are explored, the time complexity remains 1 due to the bounded nature of the problem. The mathematical justification for both time and space complexities being 1 lies in the fixed size of the sliding puzzle. With only 360 valid states and an average branching factor of roughly 3, the total number of operations and memory usage are constants. This guarantees that the algorithm remains highly efficient within this problem domain. Unlike problems with unbounded input sizes, the constraints of the 2x3 puzzle ensure that the BFS exploration and associated data structures operate within predictable limits. As a result, the algorithm's performance is both optimal and scalable for this fixed-size problem. When working with sliding puzzles, there are several common mistakes to watch out for. First, not accounting for all possible moves can be a major pitfall. This is especially true for tiles on the edges or in corners, where the number of neighbors is limited. Missing these edge cases could lead to overlooking valid solutions. Next, inefficient state representation can significantly slow down your solution. For example, using nested lists to represent the board might seem intuitive, but it introduces unnecessary overhead when hashing states or generating new ones. Instead, using tuples or strings is more efficient, as these structures are hashable and allow for quicker comparisons. Another mistake is not detecting cycles in the state space. If you don't track visited states, your search might revisit the same configurations repeatedly, leading to infinite loops or redundant processing. Maintaining a set of visited states is essential to avoid this. Additionally, using a poorly chosen heuristic in a asterisk search can drastically increase runtime. For instance, while Manhattan distance is a common choice, failing to account for the zero-tile movement constraint could make your heuristic less effective. Finally, hard-coding the board size, such as assuming a fixed 3x3 grid, limits your solution's flexibility. Designing your code to handle variable dimensions dynamically ensures it can adapt to different puzzle sizes, such as 4x4 boards, without breaking. Now, let's discuss how sliding puzzles are often approached in interviews. These problems are designed to evaluate your understanding of state space search algorithms like BFS, DFS, and S**. You should be prepared to explain the trade-offs between these methods, such as BFS guaranteeing the shortest path but consuming more memory, or A** being more efficient when paired with a good heuristic. Optimization is another key focus area. Aim to demonstrate how you reduce the search space, whether it's by pruning visited states or leveraging admissible heuristics. Interviewers also expect you to articulate the time and space complexity of your algorithm. For instance, BFS has a complexity of O, b to the power of d, where B represents the branching factor, and D is the depth of the solution. With A*, the complexity depends on the heuristic you choose, so you'll need to justify its performance. Modularity is another important consideration. Structuring your code into reusable components like separate functions for generating moves, checking goal states, and calculating heuristics not only simplifies debugging but also showcases your coding discipline. Finally, it's helpful to connect sliding puzzles to related problems, such as Open the Lock, which involves state space search in a different form, or Word Ladder, which focuses on graph-based shortest paths. These problems share underlying principles that can reinforce your understanding of sliding puzzles. In addition to the standard approaches, there are alternative methods to solving sliding puzzles, each with its own advantages and trade-offs. Breadth-first search, or BFS, is a straightforward choice, as it guarantees the shortest path to the solution. However, it can be memory-intensive since it needs to store all the states at the current level before moving deeper. While simple to implement, it may become impractical for larger boards with a vast state space. I*search improves upon BFS by introducing a heuristic to guide the search, reducing the number of states explored. This can make the algorithm significantly faster, but it requires careful selection of an appropriate heuristic, such as Manhattan distance, which must balance accuracy with computational efficiency. Another option is bidirectional BFS, which starts searching simultaneously from both the initial and goal states, aiming to meet in the middle. This approach can dramatically reduce the search space, but its implementation is more complex due to the need to synchronize two searches. Lastly, iterative deepening depth-first search, or IDDFS, combines the memory efficiency of DFS with the completeness of BFS. It does so by incrementally increasing the depth limit, ensuring that all solutions are explored systematically. However, it comes with the trade-off of revisiting states multiple times, which can increase computational overhead. Each of these methods has its strengths and weaknesses, and the choice depends on the specific constraints and requirements of the problem at hand. Great job! Today, we reviewed problem number 773, sliding puzzle, and discussed different approaches. Remember, BFS is often the go-to solution for shortest path problems. Keep practicing, and don't hesitate to tackle similar graph-based challenges. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!